Well, welcome everybody. Thank you for joining us. I'm Paul Goldbart, as Heather said, and I have the good fortune to serve as Dean of UT's marvelous College of Natural Sciences. Tonight, we'll get to hear about the exciting scientific work of an outstanding new endowed chairholder in the College of Natural Sciences and in my home department, physics. And I thank Department Chair Jack Ritchie, his team, my colleagues in the Dean's office for bringing us together to explore with tonight's speaker, the dark side of the universe. In a moment, we'll hear from Professor Katie Freese, who holds the new Jeff and Gail Kodosky Endowed Chair in Physics. Perhaps you can see my little statue of Einstein that I keep right here in my office. That's a replica of what's outside the National Academy of Sciences in Washington, DC. So I keep Einstein with me for inspiration, but for everyday work these days, I keep my model of the coronavirus spike protein nearby as well. Well, I am very pleased indeed that a participant in this evening's event is indeed Jeff Kodosky himself. And we are enormously grateful to Jeff and Gail for their exquisite gift, which empowered us to recruit Katie to Texas. Their steadfast support for UT Physics helped bring a superb scientist to further elevate an already strong department. I think we're all inspired by the impact of this gift in just the few years since it was made. Attracting and retaining talented individuals and reaping the benefits of their brilliance is possible because of the community here at UT, which provides support in many ways, including through endowment funds, which fuel many of our faculty members' most ambitious, imaginative, and potentially groundbreaking work. Our world-class faculty at the University of Texas at Austin live and dream at the sharpest of cutting edges, including seeking answers to what are unarguably the universe's biggest mysteries. What is dark matter? What is dark energy? Deeply alluring riddles, even for those of us who, like me, have studied the subjects only as enthralled amateurs and whose professional work is limited to 5% of the mass energy roster of the universe, the ordinary atoms and molecules, and the not so ordinary ones. Of course, atoms and molecules make up air, water, plants, animals, us, 100% of life on Earth. So why ask about the rest of the universe, especially now? Well, with the coronavirus raging, economic challenges, political divisions front and center, I find myself as absorbed as ever in these grand questions, transcendent elements of our human culture, to relish in difficult times as we cheer on the astrophysicists on their journey and cherish our connection to a cosmos almost unimaginably larger than we are. I'd like to dwell on this point just for a moment, if I may, and recall a sensation I had about a year or so ago when I was last at UT's tremendous McDonald Observatory, among many other things, a central site in the quest to understand dark energy. I found myself close to tears, realizing that the ground I stood on and the built structures around it form a kind of sacred space, one of a small handful of portals scattered across our modest planet through which our cosmic guides, the astronomers, reach out and connect us with the heavens, bringing them into the realm of the explored, the understood, the familiar, and yet no less breathtaking. I was and remain filled with awe and admiration when I wonder how it can be that from this thin, fragile, unexpected biosphere of life, so much has been revealed in so short a time. What better reminder of the power of science, of what we're all counting on to deliver us from COVID. And what a joy tonight to wrap our minds around the breathtaking possibility of understanding our dark universe. We'll do this as we celebrate our outstanding colleague, Dr. Freese. Katie, we're delighted to hear from a researcher of your caliber, a world leader, and a world-class communicator. We celebrate too the impact of the Kodosky Chair. I want to emphasize to Jeff and all our donors what an enormous difference you make in the capabilities of our faculty, their students, and all people who benefit from the science that happens here. Our donors are a vital part of the trajectory of discovery that starts here and goes on to change the world. Each investment in UT Science has the potential to return spectacular dividends, not only for Texas, but for all. Numerous endowments like this one offer everlasting gifts to our university community in the form of scholarships, support for experiential learning opportunities, talent recruitment, and the new initiatives that the world demands from a university like Texas. We are a stronger College of Natural Sciences for this generous support, and we are truly grateful for it. Well, it's now my pleasure to introduce our featured speaker. Our Jeff and Gail Kodosky Endowed Chair and Professor in the Department of Physics, Katie Freese, works on a wide range of topics in theoretical cosmology and astroparticle physics, including working to identify the dark matter and dark energy that seem to permeate the universe. She's also working to build a successful model of the early universe, the time immediately after the Big Bang. Before joining UT, Katie was director of the Nordic Institute for Theoretical Physics and guest professor of physics at Stockholm University. A member of the US National Academy of Sciences, elected just a few months ago, one of the highest honors in academia, Katie received her BA in physics from Princeton University, her MA from Columbia University, and her PhD from the University of Chicago, after which she held postdoctoral fellowships at Harvard, Berkeley, and the Institute for Theoretical Physics in Santa Barbara. Katie has published many papers, served on many international scientific committees, and has been honored with numerous awards, including the 2019 Julius Edgar Lilienfeld Prize from the American Physical Society. It is my great pleasure to turn things over now to Jeff and Gail Kodosky Chair, Katie Freese. Katie.
Paul, thank you so much for this wonderful introduction. And now I have to ask, can everybody see my screen? Can you see the slides?
I certainly can.
Okay, all right, wonderful. So I have behind me an umbrella of the things I don't work on. I am not working on constellations. I'm working on the stuff you cannot see. But I did want to start with some reminiscences about how I came to Austin. I had a sabbatical in 2012 in Austin, and I really enjoyed everything about it. So of course I enjoyed the city. I especially enjoyed the physics department, the theory group on the 9th floor, the Weinberg lunches on Tuesdays hosted by Steve Weinberg, all the other faculty in the other fields that I met. And I thought, wow, this is a fabulous place. So here I am, I've moved to Texas. And I have to say that major influence on my decision to come was the wonderful chair, Jack Ritchie, the wonderful dean that who we just heard from. And also, I have to say thank you to Jeff and Gail Kodosky for the endowed chair that I have. And I've met Jeff at a really nice dinner, and I hope to meet Gail as well. So thank you so much. And I want to tell you a little bit of what I work on. I want to start by thinking about the big picture of cosmology and how far we've come in the past 100 years. Throughout human history, people have wondered, where do we come from? Where are we going? What are our surroundings? What is the universe made of? And there were creation myths for every culture. And the amazing thing is that 100 years ago, starting with the brilliant insights of Einstein's relativity in 1915, we have a creation story, the hot Big Bang. And the difference is that it's right. So we've nailed it. I mean, it's incomplete. There's a lot more to work on. But the idea that we have a big picture of the universe is and the amount that we've learned in this 100 years is just absolutely phenomenal. So starting with these insights of Albert Einstein, other people applied the theory to the universe as a whole. They took the equations and asked, well, what about the universe as a whole? And they realized that there were several possible solutions to the equations. The universe could be expanding, contracting, or static. And the fact that the universe is smooth on large scales was an assumption about the symmetries of the universe. And then Einstein liked the idea, well, let's add another symmetry. Let's have a static universe. So that's what his favorite model was. But, well, nature trumps the beauty of a theory. And in this case, it was Edwin Hubble in 1929 using the telescopes at the Mount Wilson Observatory above Pasadena, who made amazing discoveries. So he was the first to actually show that there are other galaxies beyond our own. It's amazing to think even at the time of Einstein, we didn't know that. The astronomy at that point was really quite primitive. And then he looked at light from those galaxies at various distances away from Earth and realized that the light waves were not the same at the time they were emitted as at the time that we look at them. So you have atoms that give off light of particular wavelengths, and then you look at and you know what those atoms are, and then you look today, and he realized that that wavelength, you know, I have a problem. My mouse jumps. I don't have any, there's not much I can do about it. So my apologies in advance. So he saw that the wavelength was expanding, and the conclusion is that the universe is expanding. It's as though you drew on the surface of this balloon, you blow up the balloon, and of course the wavelength stretches. So Einstein at that point abandoned the idea of the static universe. So indeed, galaxies are moving apart from one another. The universe is expanding. The view that cosmologists have of the Big Bang is that it started 14 billion years ago in a primordial soup of quarks and leptons and other particles. And these initially were very, very tightly packed together. It was a very hot, dense early universe. And then as time went on, the universe cooled off and expanded. So I've shown here these particles moving apart from one another as the universe cooled off. And I like to show this picture because this is our raisin bread model of the universe. So imagine that the raisins here are analogs to galaxies in the universe. So if you have a dough of raisin bread and you put it in the oven, then the dough rises and the raisins move apart from one another, not because they're doing anything, but just because the underlying bread is expanding. So it's the same idea for the expanding universe, that things are on the average moving apart from one another. Now, one major difference between this raisin bread and our universe is that the raisin bread has a central point, whereas the universe, as far as we know, does not. So now let's look backwards in time. And in that case, everything is getting more and more packed on top of everything else. And so everything in this room is going to condense to a point. And yet it's possible that the universe is infinite. In fact, that's our best guess. So if that's true, then no matter how close things get closer and closer, things get together, there are still things out at infinity. Eventually, what we mean by the Big Bang is not that you've reached a single point, but instead what it means, the density is so great that we lose our physical description. We need a theory of quantum gravity that we don't have. And so maybe string theory or other theories will answer the question of how can we go farther to a more dense time in the universe. So the Big Bang is not a point in space. You can think of it as a point in time. It happens everywhere at once. There's no explosion, but if you want to have one, then put one everywhere in the universe. So where do we stand in cosmology? Well, we've had a lot of big questions answered, certainly in the last 100 years, but even more at the turn of the millennium. We know the geometry of the universe. We know the total mass and energy content of the universe. We know the age of the universe. But many of the other big questions remain, which includes the one I'm talking about. What is the universe made of? What is the dark matter? What is the dark energy? So I wanted to go back to this big picture of the universe. That there were in principle 3 possible shapes for the universe. It could, if I draw 2-dimensional analogs, we could have been living on the surface of a higher dimensional sphere, the entire universe being there, or on a saddle, or there could be a flat geometry. And I don't mean 2-dimensional, I just mean that there's no curvature to the universe. So there were, at the time of the 1930s, 3 possible geometries, and one of the holy grails was to figure out which one's right. And so what I mean by geometry is, well, if you have a flat geometry and this guy shoots off 2 parallel lines, well, they remain parallel, which is what you learn in 8th grade geometry. Whereas if you're living in a saddle universe, then those rays would diverge, even though you thought you were sending them out in a parallel fashion. Or the other possibility, in a closed universe on the surface of the sphere, you send them out and they diverge, and then they come back and bite you from behind. So as I said, in 1930, there were these 3 possible geometries, but now we know what the answer, and that is that the geometry of the universe is flat. I wish these slides would stop jumping. So the way this was discovered by looking at the leftover light from the hot early epoch of the universe. This is the cosmic microwave background. So if we look in the cosmic microwave background sky, if light was traveling in straight lines, then that would tell you about the size of the hot spots and the cold spots in the microwave background. And so the prediction was, if these hot spots that are hotter than average are about 1 angular degree in scale, then that would be consistent with the flat geometry. And look at this. There's no arguing with that. That's a big deal. That tells you the geometry of the universe is flat. Yes, indeed. And then from that, oh, I just wanted to reiterate what I mean by flat geometry. I don't mean two-dimensional. In fact, if you take a cube, all these sides would go out to infinity in any direction. I just mean there's a flat geometry, no curvature required to explain the universe. Well, now we know from Einstein's relativity that the geometry on the left hand, these are Einstein's famous equations. It's the only slide with equations I'm going to show. So in relativity, on the left-hand side, you've got the geometry, and on the right-hand side, you've got the mass and energy content of the universe, and they're related by these equations in the same way that you've often seen these pictures where here's the Earth bending the space-time geometry around it. So from the geometry of the universe, we know the total mass and energy content, and this is the answer. It's this number, 10 to the minus 29 gram per cubic centimeter. And I guess that's the density of outer space. And I'm going to compare that to water on Earth, which is 1 gram per cubic centimeter. And ask me later, I'll tell you how I tried to explain this to the Queen of Sweden and failed miserably, but it was very funny. So before I leave this subject, this is again the same data. And there we go, the initials of Stephen Hawking in this microwave background data. This is from a different satellite, but it's the same data. So now let me turn to the question that I work on, which is, what is the universe made of? And here we have this very surprising result that if we take all the objects of our daily experience, our bodies, the chairs we sit in, cocktails, include the entire Earth, include the entire stars, the sun, and so on, well, that's all made of atoms, as we know, which are made of quarks and so on. But all of that stuff only adds up to 5% of the universe. That and leaves us wondering, well, yeah, what about the rest? And in particular, I'm going to talk today mostly about the dark matter that makes up 25%, with the dark energy making up the rest, the 70% remaining. So this dark matter problem actually is 80 years old. So it's perhaps the longest outstanding problem in all of modern physics. It dates back to the 1930s to Knut Lundmark in Sweden, and Fritz Zwicky, a Swiss scientist working also in the telescopes in California above Pasadena. So I'll tell you about the famous results of Fritz Zwicky, who looked at a cluster of galaxies, and he noticed that the galaxies moving around the center were moving far too rapidly. He couldn't explain, why are they going so fast? There's nothing, the other galaxies aren't pulling on them enough to do that, so the stellar material can't explain it. So the proposal is to add in additional mass, dunkle Materie, as the explanation, and this is the German for dark matter, and by dark, that just means it's not stars, it doesn't shine. Okay, so I have a lot of stories that I'm dying to tell, so I'll tell you what he said in his book about his colleagues. He said they're all spherical bastards because no matter what direction you look at them from, they're still bastards. Okay. So the idea of dark matter was out there for a long time, but it was really the work of Vera Rubin that nailed it, that led to the scientific consensus that dark matter is there. And the reason for that is that she looked at galaxies and found that all of them have dark matter in there. And I wanted to show you how that argument works. So let me switch. This slide has nothing to do with dark matter. It's the idea that's going to carry over to dark matter. Let's look at the solar system. So let's start at the center and then move out. We're going to look at planets moving at different radii as you move away from the sun. So the sun is at 0. And this is how fast they're moving. So the fastest one is the closest one, Mercury, Venus, Earth, Mars, and so on. And I was supposed to remove Pluto, but instead I added another planet. So there you go. Now I've got 10 in there. And I left it because I thought it was funny. So then there's a simple formula that explains how these things scale as you move out to different radii. And what you see in here is this is the mass of the sun. So if the mass of the sun were bigger, then these things would be moving faster. So by studying how fast things are, you can learn about the mass interior to their radius. So this shows the idea. And it was Tycho Brahe who made a lot of these planetary measurements. And he lost his nose in a duel and wore a gold and silver replacement. He also, there was a lot of discussion about how he died. So I'd always heard that he died of a burst bladder at a dinner with the king. But it turns out that people started speculating that it was mercury poisoning by Johannes Kepler. So Kepler's laws perhaps should have been Brahe's laws. Kepler was the student of Brahe. So believe it or not, they actually dug up his body about 15 years ago and analyzed the mustache hairs that were still there, and there was no mercury poisoning. So I guess the burst bladder story was true. Okay, let's get back to dark matter now and talk about the same kind of rotation curve, but this time of galaxies. So how fast are things moving around the center of the galaxy as I move out at different radii away from the center? So again, the same thing is true, that the orbit of a star here is determined by how much mass is inside that radius, interior to the orbit. And again, things are moving too rapidly. So this is the same picture I showed for planets, but this time I'm showing it for a galaxy. So based on the stars inside the galaxy, then you would get this curve, so that the speeds should be dropping as you move out from the center. But instead, what Vera Rubin and company they found that these are flat rotation curves. There's something else that's pulling on these stars and speeding them up. So if you add in additional dark matter in the form of a halo, I'll show you a picture in a second, then it all adds up, it works out. So I'll use as an example our galaxy, the Milky Way. And at the center, shown in yellow here, just so you can see it, is a supermassive black hole, which is the origin of the 2020 Nobel Prize in Physics. So Andrea Getz and Reinhard Genzel, they were the ones who proved there has to be a supermassive black hole in there. And that supermassive black hole weighs 4 million times as much as the sun. These things, they saw things moving rapidly around that black hole, very, very close in, so they were able to prove it. And that leads me to relativity at UT Austin, which has an illustrious past, including Wheeler coining the term black holes and the DeWitts, and people who are here now, including these 3 recent hires, Aaron Zimmerman, Deirdre Shoemaker, and Pablo Laguna, and Richard Matzner, who is also in relativity at Austin. So I just want to emphasize the supermassive black holes are not the dark matter. People tend to think black holes and dark matter are the same thing, but that's not true. So every galaxy has one at the center, but they only make up a tiny fraction of the universe as a whole. So let's go back to the picture of the Milky Way, and you see these pinwheels. These are spiral arms where all the stars are, including the sun is along one of these. So, and then we take this whole thing, look at it from the side, and this is what it looks like. So this is that disk of where the stars are, and from the center of the galaxy, the sun is 25,000 light years away. The galaxy as a whole weighs 10 to the 12 solar masses, so the black hole at the center weighing 4 million is really small compared to the entire galaxy. So an artist's rendition of what our galaxy might look like is this, which is also, look behind me, I've got it going behind me as well, although there's too many stars outside of these. So here's that spiral star structure. And then there's this giant spherical thing that we call a halo of dark matter. So the first way that it was discovered was through the rotation curves, things moving really rapidly. Another way is Einstein's gravitational lensing. So another way to detect dark matter is, well, dark matter doesn't give off light, but it bends light. So no matter what mass you have in here, this is a massive compact halo object, but whatever the mass is, if in our telescopes, we look at some distant star and the light from that star is bent or lensed on the way to us. So we might wrongly think the star is over here, but then we would notice 2 things. We would notice, we have multiple images of the same thing because it also went the other way around. And we'd notice that this light is sheared. And based on the mathematics of taking what we observe and using math, we can figure out how much dark matter is on the way between the star and us. So in fact, there's an app you can get on your iPhone written by a Michigan student, which has the right equations of gravitational lensing. So you can lens yourself more and more and more. But let's go to real data now from Hubble Space Telescope. So there are distant galaxies, very bright, that are being lensed by dark matter. And you can see that, look at all these sheared multiple images. And what you do now is use a computer to reconstruct the density distribution between the distant galaxies and you. And when you do that, you get images like this. Now, this image does not correspond to the same data that I just showed, but it's also from Hubble Space Telescope data. This is a cluster of galaxies. So you can see the cluster density of peaks here. These are galaxies sticking up. And then in between the galaxies, you have more dark matter inside the cluster. So we have the lensing, we have the rotation curves of galaxies. We also have the bullet cluster to show us that dark matter has to exist. And this one is interesting because it really shows the different behavior of two different types of matter. We think what's going on here is that there's two clusters of galaxies that have collided with one another. And when they do that, the gas, which is shown in pink, the gas is the stuff that gives off X-rays. And so in the same way that when you and I collide, we would not be able to go through each other because we have electromagnetic interactions, we have strong interactions that hold nuclei together. And so we would get stuck in the same way the gas did. So this is the ordinary matter. But then from lensing, there's evidence there's more matter out here. And this is stuff that these things did go through each other. So you can see that this dark matter behaves very differently from the ordinary matter. So the bullet cluster is really evidence that there's two types of mass. It's also interesting that we would not be able to exist without dark matter because we need dark matter to cluster together starting in the early universe to make galaxies. And then later on, the stuff that we're made of falls into the gravitational potentials provided by the dark matter. So regular matter can't clump fast enough, but dark matter does. So here's a simulation of dark matter particles, and they're shown in blue. And initially, they're almost uniformly distributed with slight differences. Some areas have more dark matter in them than others, and those areas will pull in more dark matter, and it clumps more and more until you get to today. And in the simulations, this is the result, and it really matches the real world quite well, where the galaxies are at the nodes, at the intersections of these filaments of structure. So we wouldn't be able to exist if galaxies hadn't formed, and we really needed dark matter in order for that to work. So I talked about a wide variety of pieces of evidence for dark matter. I didn't emphasize this is actually the biggest one of all. This is, again, from that peak we learned that the universe is flat, but from the height of the second peak, we also learned that atoms can only make up 5% of the universe. And from all the other peaks together, that dark matter is 25% and dark energy is 70%. But what we still don't know is about the non-gravitational interactions. What is this stuff? So back on this picture, let's talk about what the dark matter could be. Well, I'm going to start with things that might seem like obvious candidates, and they just didn't work, which includes gas and rocks and dust. And we even looked at small stars or planetary objects, white dwarfs or neutron stars. We looked at a lot of these possibilities which fit in this massive compact halo object category, the machos. And all of these things can only add up to a few percent of the dark matter. They don't work because you would have seen evidence from other observations. So what we're forced to is beyond the standard model of particle physics. There's something exotic going on, and we have to figure out what it is. The easiest candidate would have been neutrinos. What a shame, because they definitely exist. But the problem is that not only are they so light they would ruin a galaxy formation, but their total mass only adds up to 0.5% of the universe, so they just don't cut it. There's a lot of interesting candidates in here. Primordial black holes. We heard a talk from postdoc Nicola Bellamo yesterday because people are interested in those again because they could explain LIGO data. Paul Shapiro works on scalar field dark matter. John Killich on a number of dark matter candidates, including asymmetric dark matter. What I want to focus on, though, are the top two candidates for dark matter, the WIMPs and the axions. And the reason that I say they are the top 2 candidates is because for both of those, cosmologists didn't have to invent these particles. They're already there in particle theory for other reasons, solving problems. So axions were originally invented by UT Steve Weinberg, and then a variant that is still the one being considered the most today by Willy Fischler. And these are an outgrowth of a solution to a problem in the theory of strong interactions that hold our nuclei together. So in that solution, you automatically get these particles coming out, these axions. They're very light, and yet they're non-relativistic. They're moving slowly. And this is a very active area of research on the experimental side. So this is a plot of the axion mass versus the strength of how axions interact with other things. And you can see all of these efforts going on. It's kind of amazing. So in order to solve this problem of strong interactions, you have to be in the yellow band. And in particular, this ADMX experiment is going to be probing a particularly interesting region here. And there's a review of my former postdoc about all of this if you're interested in reading about it. I'm going to focus instead on the WIMPs, which are the other highly motivated candidates. So these are weakly interacting massive particles. I like to joke that the WIMPs have beat the machos. So the idea of, I wish this would stop. Anyway, so if this idea is right, there would be billions passing through your body every second, with somewhere between 1 a day or 1 a month hitting one of your nuclei. But as I said before, they don't have strong forces or electromagnetic forces. And so they're not going to do any damage to you at all. So yes, they do feel gravity. And there are 4 fundamental forces. And of the 4, there is one other possibility, and that is weak interactions. So that's the idea. We asked the question, well, what if dark matter had weak interactions? And by the way, they weigh about 1 to 10,000 times as much as protons. So I want to tell you why we think these WIMPs are good candidates. And one reason is, as I mentioned, they're already there in particle theories, which is, in this case, supersymmetry, an extension of the standard model where every particle we know about has a partner. And these supersymmetric partners are unstable. They decay to lighter and lighter and lighter ones until you get to the lightest supersymmetric particle. And that may be the dark matter. That may be a WIMP. And the second reason that we favor WIMPs as good dark matter candidates is that you get automatically, with only the ingredient of weak interactions, you get the right abundance remaining today. So this was work in 1977 of Lee and Weinberg, where they showed, this was for neutrinos, but it's very similar because neutrinos are also weakly interacting. And so it's this regime up here that we're looking at when particles weigh more than a proton, then you want it to get the right abundance, you have to be below this green line. And so indeed, it's this region over here that's interesting as far as solving the dark matter problem. It works out automatically if you have weak interactions. Well, it's nice to have a good theory, but you have to go and test it. And so there's a 3-pronged approach to doing that I would like to tell you about. So this is really the same diagram, which I'm sort of plotting, if you read it from left to right, in 3 different ways. And let me tell you first about using accelerators to do it. So the Large Hadron Collider at CERN is a 17-mile ring where proton beams are accelerated in opposite directions at nearly the speed of light, and they collide at 4 intersection points where the detectors are located. So the 2 that we're particularly interested in for the experiments here well, one of them is the ATLAS detector, and here's Fabiella Gianotti, she's now the Director General of CERN. And UT has an ATLAS group, including these 2 faculty members, Tim Andine and Peter Onisi. This is how giant these experiments are. And here's somebody standing there. These are really great achievements of humanity to build these things. Here's Peter Higgs in front of the other experiment, the CMS experiment. And sure enough, the LHC's first success was discovery of the Higgs boson that weighs 125 times as much as a proton. A proton weighs a GeV. So that was the first success of the Large Hadron Collider. And now the second major goal is search for new physics, including supersymmetry and dark matter. And what you would see there if two protons collided was a string of supersymmetric particles decaying until the lightest one escapes detection. And you have to look for that missing energy plus jets from these other things coming off. Nothing seen yet. So particle masses being pushed to higher masses, and we'll see what comes of that. Now, a second way to search for WIMPs, this is something I was involved in from the very beginning, is direct detection experiments. So here you have a nucleus, and this time this is an astrophysically, you're taking advantage of the fact that you've got all these WIMPs flying around in the galaxy. As I said, billions going through your body every second. So if you build a detector, the WIMPs will hit that detector and deposit some energy, and that's what you're looking for. These are very, very small energy deposits and very, very slow count rates, very, very tough experiments. So we were among the first to propose that you should do this. So I did the calculations of the scattering, and David Spergel thought about, well, what is the distribution of these particles in the galaxy? And was Andre Durkier who got us thinking about it, because he'd been doing the same kind of thing for neutrinos. And we were the second paper to do that with WIMPs. Now, these detectors have to be in underground laboratories. So this is an example of the Gran Sasso tunnel underneath the Apennine Mountains outside of Rome. And since we did these calculations, we convinced people to build detectors, and it's now a worldwide effort. And well, I have to admit, it's frustrating. There's only one experiment, the Dama experiment, in that same tunnel that I showed you that has a positive result. And I'm going to tell you about that. This is a puzzle. So the origin of the result is an idea that we had. The sun is moving around the center of the galaxy, and that makes it look like you're moving into a wind of WIMPs. It's just like when you're driving, it looks like the rain is coming into your windshield. Now, on top of that, the Earth moves around the sun, which means that the relative velocity between us and the wind changes with the time of year, and the count rate should also change with the time of year. So we realized you'd expect a maximum count rate in June and a minimum in December, and that is exactly what they see. This is only a fraction of their data. It goes on for years and years, and and they're made of sodium iodide crystals in that tunnel that I showed you. And I don't know if you know what 12 sigma means, but I think that's, like 1 in 10 does that means it's real. Okay, they are seeing an annual modulation. The question is, what are they seeing? Is it WIMPs or something else? And there's two problems. One is they won't release their data to the public, which is very unusual. It's very unusual. And the other one is that other experiments have no signal. Now, here's the problem. The other experiments are made of different detector materials. And I just have to show this. There's a lot of interesting characters here too. So you have Juan Colliar saying about Eleanor Prile, who's the PI of Xenon, and Rita Bernabe, the PI of Dama. I'm a Spaniard caught between two Italian women. So we have fun. So now I'm not sure I want to spend a lot of time on this. This is an out-of-date slide that makes the point that if you want to match Dama, you have to be in the green regions. This is the mass of the particles versus the number of events you'd see. But then you also, in order to explain the Xenon experiments, you have to be below the green and red lines. But in order to make this plot, I had to assume very specific interactions that depend on atomic mass squared, and so that assumption may be wrong. So we don't know how to plot things on the same curve, because they're made of different detector materials. So we don't know if we should be making these plots, but we certainly enjoy our meetings. So it's an unexplained signal still there as more than 13 years. I don't even know how many. And now what's happening is it's going to be tested because other groups are using the same material, Cosine, Saber, and Anais. And this is what's exciting, is that Cosine already has 2 years of data, and they kind of see a peak. This is this is June here, and so yeah, they see a peak also in June. But statistically speaking, we don't know yet what's going on. But give it another few years, and we'll know whether Dama is confirmed or ruled out by this other experiment. I have to tell you how excited I am that Kim Boddy has now come to UT as a new assistant professor. She's awesome. She works on all types of dark matter problems, including, she noticed something that we did not. What if dark matter interacts so strongly with ordinary matter that it cannot get through the Earth down to the underground detectors? Okay, so she realized, well, but it would affect the cosmic microwave background, it would affect the galaxy abundance and so on. So very interesting. And I'm very excited. The nucleus, we have now a nucleus of new efforts in cosmology at UT Physics. And oh, did I mention the astronomy department at UT is great, and there's people there doing cosmology as well. So you know, the trouble is that I don't have too much material, but I got to tell you about some of the new ideas we have for dark matter detectors because they're too much fun. Okay, so one of them is, by the way, this picture is something you can buy from Illumina Inc. for 200 bucks. There's a nanometer thin plane of gold with DNA strands hanging down. And what we would do here is if a WIMP comes along and hits a gold nucleus, then the gold nucleus gets knocked forward, breaks the DNA. But the beauty of DNA is at that point, with these broken strands that you collect, you can make billions of copies and you can sequence them, which allows you to figure out what track the gold took, which is also the direction the WIMP came from. And once you have this kind of directionality, you can really figure out what's going on. It's going to be a lot easier to know that you've really found dark matter. So no, we cannot use the ones for 200 bucks because you have to build things much more radioactively clean than that. Another idea, paleo detectors. Well, instead of having giant tons of xenon liquid, which is what the xenon experiments are made of, what if you have tiny rocks, but they've been sitting underneath the Earth 10 kilometers down for 1 billion years, collecting tracks, being hit by WIMPs for 1 billion years. So that's another way to go with. And nowadays you have the nano tools to identify nanometer tracks. And so this is a real possibility. And people are starting to do some preliminary experiments on this. Okay, so there's another way to go, which is indirect detection. And this is taking advantage of the fact that dark matter particles annihilate among themselves, and you can look for the annihilation products, neutrinos, high energy photons, positrons, and people are doing that. And so there's all three of these are being searched for in different experiments, including ice cube at the South Pole. You have these deep below the ice. You've got looking for neutrinos, these phototubes down here. And the only one that has interesting result is the Fermi satellite, which is looking at high energy photons called gamma rays. And there are some weird ones that are unexplained. So this is the gamma ray sky that Fermi sees. And right at the center of the galaxy, there's a small spherical region that could be from dark matter annihilation. And there's a lot of discussion of that. It could also be pulsars. We don't know. So it's tough, but it's really interesting. So the possible evidence we have now is from this DAMA annual modulation, which is going to be tested by cosine 100. And then this Fermi gamma ray excess from the galactic center. So that's the experimental side of things. And then on the theory side, you have to figure out what is going on, how can you explain all these positive results, the negative results, and so on. You have to think about the particle physics, the nuclear physics. So interesting times. And I'm trying to switch slides, but now I can't. There we go. Come on. Okay, so I don't have a lot on this, but I have to tell you about dark stars. This is our baby. Okay, so this is the idea of Douglas Spolyar, Paolo Gondolo, and I. And the idea is, oh yes, this was a movie that predated us, which is, it turns out, it's a cult film. And I want to mention collaborators include a lot of UT's connections. So here's Paul Shapiro in astronomy. Pearl Sandick was Steve Weinberg's postdoc at the time in physics. And Josh Siegler is my current student at UT. And Tanya Rindler-Dollar was also a postdoc at UT. So working a lot of UT connections on this work. So here's the basic idea. It's all in one slide. The first stars to form in the history of the universe could have been powered by dark matter instead of by fusion. So that's very, very strange. So these first stars are made almost entirely of hydrogen and helium, and dark matter constitutes only less than 0.1% of the mass of the star. So these things are not made of dark matter. They're made of ordinary matter, and they're powered by dark matter. And they're very weird because there's no fusion, they don't have to be hot. In fact, they're cool. They're very big. The size of these things is this 10 times the distance between us and the sun. That's how big and puffy these things are, and very cool on the surface, which means it's because they're so cool, they can keep accreting mass getting bigger and bigger and bigger until they grow maybe even up to 10 million times the mass of the sun. If they do grow that big, then they would be really bright, up to 10 billion times as bright as the sun. And these are visible in not the Hubble Space Telescope. Well, actually, they could already be there, but they would be more, they could be found by the next generation, which is the James Webb Space Telescope. So we're very excited that when this thing launches, it's been delayed over and over again, but when it launches, we're going to go see, oh, are there dark stars in there? The other thing that's interesting about these things is that it resolves a problem. So once the dark matter runs out, these things will eventually collapse to big black holes. And that's a good thing, because nobody knows how to explain the supermassive black holes that are not only at the centers of galaxies, but even very, very, very early in the history of the universe. You've got 10 billion solar mass black holes out there. How the heck did you make those unless you started with relatively big ones, which is something that we know how to make from the collapse of the very massive dark stars, the supermassive dark stars. So in all, there's all these different ideas. Oh, I wanted to mention on the dark stars also one more thing. It doesn't have to be WIMPs. We're looking at self-interacting dark matter, also interesting possibility for power, for the power source. So anyway, we talked about all these different ways of doing WIMP hunting, and let's hope it works out. And well, keep you posted. So to conclude, I'm going to make just a few remarks about the 70% dark energy that we really don't understand. You might as well call it gobbledygook for all we know. The one thing we do know is that it is very different from matter. Matter causes things to attract. So that's why galaxies and ordinary matter, it's all gravitationally attracted. But what's observed is that there's something causing the universe to accelerate. So it's some kind of repulsive force. So the dark energy it's very different from matter. It has the opposite behavior, something repulsive going on. And we're trying to understand it in terms of a vacuum energy, cosmological constant, or other possibilities. And one of the things that observationally we will be able to test is it a constant or is it changing with time? And that'll give us some information on the observational side. Very tough problem. So indeed, we know that galaxies are not just expanding, but also accelerating apart from one another. And I'm going to conclude with a joke. So this was at the World Science Festival in New York. The three of us on this panel, we were talking about dark matter. And these three were talking about dark energy. And I made a statement, which is the only true thing that we know about dark energy. So I hope you get the joke because I'm going to stop there. This is I have a book for the public called The Cosmic Cocktail, 3 parts dark matter, and I've got inside it I've got the cosmic cocktail recipe from a 10-ounce drink. Here's what you need. You actually only need 2.5 ounces dark matter, but I rounded up. And as I said, supermassive black holes are tiny. They're only a millionth of an ounce. And in the early universe, the whole thing would have been shaken up by constant interactions. And okay, last slide. I added this last minute. Because of my time in Sweden, I've gotten twice to go to the Nobel Ball. And so I was very excited to get to go to that. So I decided to add that in the last minute because it's fun. But let me finish with this slide. And I think I should probably stop sharing, because then people might want to ask questions and I can see them.
So Katie, first and foremost, thanks so much for a layman's talk that I was actually able to grasp. I have somewhat of more of a personal question. What burning question do you want to answer as a physicist that you would consider your career? You've done it, you've made it. What's driving you?
I mean, look, if we figure out what the dark matter is,
that
would make me I'll give you 2 answers. One, we figure out what dark matter is. That's really driving us nuts. And the other one is discover dark stars. I would really like that to happen. And then, I haven't talked about inflation, which I also work on. And I really think the model of natural inflation, which was something we proposed some time ago, I think it's a good model and it can be tested too. So I give you those 3: dark matter, dark stars, and natural inflation. Just one of them, please. That's the trouble of being a theorist. You can have great ideas, but nature does what nature does.
Well, thanks very much indeed, Katie. Really inspiring. And we have a little time for questions, so people should just fire away in the chat, and Heather and Marielle will read them out. I'm going to begin just by asking you what WIMPzillas are.
Okay, so they are very, very heavy particles. They are 10 to the 17 times as heavy as protons. And they arrive at there's an early period of accelerated expansion called inflation. And since during the universe was vacuum dominated very early on, but then it somehow switched over to having the normal stuff that we're made of. And it's in that reheating process that these WIMPzillas would have formed. And that's the basics.
Thank you. Good. Heather and Marielle, do you want to take over and read the questions?
By the way, in my book, I tried to put a picture of Godzilla to go with that, but you can't get the copyright.
Sure. Well, we have a question here. I'll read it out. What are your thoughts on the Hubble constant conflict?
Oh, yeah, that's a good one. So let's back up. When I was in grad school, let me back up even more. The Hubble constant, that tells you that is the expansion rate of the universe. And when I was in grad school, people were arguing, is it 50? There was one camp that said it's 50, and the other one said it's 100 in units of kilometers per second per megaparsec. That's the expansion rate of the universe. And each was absolutely certain. Well, guess what? The answer is pretty close to the middle. So we know it's around 70. However, there's something very weird, which is there are early measurements of the Hubble constant that come out of this cosmic microwave background, the leftover light from the Big Bang. And from those measurements, all of those measurements, the different experiments, they all get like 68. Whereas if you do late time measurements from supernovae and from many other things, then you get numbers like 72. So this may not sound like a big difference compared to 50 and 100, but we're talking about statistically seriously significant differences. And no one can figure out what's going on. So then, of course, people have tried to examine, well, what can I do to change the universe to give me these two different answers? And so there are solutions that would be from before the formation of the cosmic microwave background. Those are called the early type solutions, and there are late type solutions. And there's a paper that I can send you to that tells you why none of them will work. However, there is one holdout, which is Mark Kamiankowski is going to be our colloquium speaker in a few weeks. He was the postdoc advisor of Kim Boddy, and he had an idea for early dark energy as a solution. So I thought that had been ruled out, but I'm very curious to hear the colloquium, because apparently it's one of the, you have to do things very close to the time where the microwave background was formed. So it's not a natural solution by any means, but if there was anything at all, we're all listening. It's a tough problem.
Very good. Thank you.
That was
go ahead.
Kind of a long answer.
No, it's great. I'll leave it to you, Heather.
Okay. Can you speak about what impacts our ability to observe dark stars?
Oh, well, these are very early objects. They would have formed, let me back up. So when the universe was about 200 million years old, which is nothing in the grand scheme of things because we're now at 14 billion, that's when the first stars started to form. And there would have been collapsing clouds of hydrogen very near the centers of protogalaxies. And there's a lot of dark matter right there, which is why this dark matter power could be really important in these early stars. Whereas today, the sun, for example, we're not at the center of the galaxy. We're too far out. And so the amount of dark matter out here is not enough so you can collect dark matter, and these are tools to search for dark matter, the particles that would be inside the sun, but not enough to power the sun. So these so it had to be very early stars. And that means you have to have telescopes sensitive to these early times. And the Hubble Space Telescope can go out pretty damn far, But the James Webb Space Telescope is an infrared telescope, so it can go farther back in time. That's what we're waiting for. Does that answer your question?
I will let them post in chat, but next one, do all dark matter candidates allow for dark stars? And if not, how else might supermassive black holes form?
So, so as far as dark stars go, axions do not work. I wish, but they don't. You somehow, what has to happen is the dark matter that's inside this collapsing cloud of hydrogen has to impart energy to the hydrogen somehow. And so for WIMPs, the annihilation of the WIMPs, well, the annihilation products includes electrons and positrons and photons that get stuck inside this collapsing cloud. So it thermalizes with and heats up the cloud. So the axions, there's no way to do it. Now with self-interacting dark matter, we think we also are going to be able to do it. And we haven't really investigated other candidates. So I don't know so I can't answer that question generally, but we're looking into it.
Great. One of the great topics in physics is the seemingly eternal search to explain the cosmos as new phenomena and particles are discovered. Does it seem to you we are in an everlasting game of whack-a-mole?
Well, yeah, that's the fun part. Absolutely. How disappointing if we had it all figured out. I mean, it's just amazing how much we do know. I mean, there's an edge to the observable universe, which is set by the fact that it takes a while for light to get to us. So for example, we're not looking at the sun right now as it is right now. We're looking at the way the sun was 8 minutes ago, because that's when the light left the sun that we see. Of course, it's getting dark, but you get my point. Then, so the same is true that light that left 14 billion years ago, that would have been the beginnings of the universe as we know it. So that is as far out as we can see, because telescopes are like time machines. We can, as the stuff that is 14 billion light years out came to us from the time of the Big Bang. So I forget where I was going with this. Oh yeah, this is how much we do know. I mean, it's unbelievable. So do we feel like we know the basic physics all the way out into the observable universe? Not that we know what it's made of. We don't know the dark matter, dark energy, but we know the physical laws. We're looking for more. Maybe there's a fifth force. We're always looking for new things. That's what's it's fun. It's exciting. We'll never solve all the problems. It's fun. The search is the fun part.
Great. Have researchers thought about whether dark matter could be explained by symmetry breaking happening in different ways in different parts of the universe?
I'm not sure I know how to even start with that one. Okay, so well, you know what? If symmetry breaks in different regions, you can have domain walls between. So there's a phase transition. You have a domain wall where something takes on one number on one side and one number on the other, and there's a lot of energy sitting in the domain walls. And so yes, people tried to see, can you do dark matter with that? And the answer is no. In fact, if there were big domain walls, then the micro background would be affected in a way we could see. So we know they're not there. But more interesting is domain walls as a source of dark energy, because that's actually how they would function. They would cause repulsion, which is really interesting. But unfortunately, they're just not there as far as we can tell. So your question, I think I did answer your question.
Peter Riley, did you have a question? And if you want to unmute, you can ask Dr. Freese.
Hi, Peter.
Hi, can you hear me?
Yes.
I have a question which maybe is very naive, but I'm wondering, as you probably aware, UT is conducting this dark energy experiment by Carl Gepper.
Yeah, at HETDEX.
And I'm wondering if apparently they're seeing quite a few, I guess, very early black holes.
They're finding one thing that Carl has found is intermediate mass black holes, which people are arguing all the time. Are they real or not? So
galaxies, apparently not unaccompanied by galaxies.
Oh, I see. Okay, yeah. Mm-hmm.
And I'm wondering if I'm assuming they're fairly early, because they're looking, I think, and mostly I still think they're looking at the Lyman alpha line, which is from 3 to 6 billion years.
Okay, you know what, Peter? I'm going to have to talk to him about this.
Yeah.
Because yeah, this is interesting. I mean, there are some, everybody thought that black holes made a small fraction of the mass of galaxies, but there's some galaxies that are almost entirely black holes. So, and now finding isolated black holes, not even inside galaxies, that's, wow. Okay, so I'm going to have to talk to him.
Yeah, thanks.
Katie from Joseph Smith, when using gravitational lensing, how do you differentiate between interstellar gas and dark matter? And can you subtract out the effects of dark and compare it to general relativity predictions?
So what you get out of lensing is the existence of dark stuff. So then if you want to differentiate, then I guess you have to go look for the gas. Does it shine in the X-ray or some other way of identifying it? Because simply by the lensing, its mass just bends light. Doesn't matter what the mass is. So you'd have to look for it another way. And I didn't really understand the second half of the question, so I'm not going to answer it.
Okay, from Keith Chen. Given the tremendous power of big data and AI, any new discoveries based on these alternative research methods in the area of cosmology?
Okay, so this is a field that is just getting started. And I think it's incredibly exciting. And I think UT should hire in this area and make do a cluster hire, You can tell I'm really excited. I'm not trying to tell UT what to do, okay? But I just think this is the way of the future. It's incredibly exciting. And it's just getting started. So not yet, but we shall see.
Sorry, Casey, my audio went dead for a minute.
So this looks like our last question, Katie. What's your opinion? Hiring committee future. What's your opinion on the various exotic matter candidates, and do you have any favorites?
I didn't show all of them. In fact, there are dark matter candidates that go all the way from 10 to the minus 22 eV. Remember, a proton is 1 GeV. So this is really, really tiny, up to the Planck scale of 10 to the 19 GeV. This is 40 orders of magnitude. The lightest being fuzzy dark matter, which if you associate that with a wavelength, would be the size of the galaxy. So what I find interesting are things that have theoretical motivation. So that's why I really, really like WIMPs and axions. The other stuff is there are people who are very excited about alternative candidates, and experiments are going to get built to look for them. And I think that's great. But I'm just telling you my personal preference. Oh, I rather like primordial black holes too, actually.
Well, I want to just take a minute to say thanks again to Heather and Mariel and their team. Thank you, of course, to Katie and to Jeff Kadosky. Thanks to everybody for joining us. I can hardly think of a better way to spend an autumn evening.